Greetings. Today we're going to start talking about microservices. So, in a presentation like this, I obviously can't cover the vast topic of microservices, and I'd rather sort of show a lot by example. And so I don't want to spend a lot of time just on slides, but I do think that going through some cursory information just to make sure that we're all sort of on the same starting point is really important when it comes to microservices. So, microservices. What is a microservice? I've looked up a lot of different definitions and tried to basically coalesce what I thought were the best bits from them. And so, an autonomous, cohesive, small set of related functionality. So, we're going to talk in the slide deck here. What do we really mean by that? What does it mean to be autonomous and cohesive? I think a small set of related functionality makes some sense. Each microservice should have functionality that is related to each other, and ideally microservices are on the smaller side, and we'll talk about why small is good. Microservices can be changed and deployed separately from each other. Updates to one microservice should not require immediate updates to any other microservices, so that's actually a really big deal. If you start to decompose a monolithic application into microservices, and what we're saying here is there should be the ability, if we've successfully implemented the microservices correctly, to update one of those microservices without forcing an immediate update of the other microservices. So one way that happens, so there obviously could be changes, right? Like the new microservice could be introducing some new API endpoints that are the preferred way to call the microservice in the future. But what you have to do is make sure you're still backward compatible, because we're not saying that the deployment of a microservice can't require eventual changes in other microservices. We're just saying when a microservice is updated and deployed, it should not require an immediate change, because otherwise you're coupling the microservices together and you're saying that if this microservice changes, these others have to change as well immediately, which is really losing one of the main advantages of microservices is the autonomy. And that's one of the first talking points around autonomy, is we should be able to change this microservice without having to force other microservices to change with us, so that when we go to deploy our changes, we're not saying we don't have to coordinate with another team that might own other microservices. And so that really comes down to the golden rule here. I took this from a book, Building Microservices by Sam Newman. Really love this statement that he has in the book. It says, can you make a change to a service and deploy it by itself without changing anything else? And if that's the case, you've successfully implemented your microservices. If when you go to change and deploy a microservice, it does require somebody else to be updated and changed at the same time, you have not implemented microservices correctly. All right. So what are some of the advantages of microservices? There's a whole bunch, but I really tried to keep this list rather concise. But smaller independent services equals smaller independent, more frequent changes and deployments. So if our microservices have a smaller footprint in terms of what they're in charge of from a feature point of view, we can change them more often when we go to write tests, right? So in good development practices, we should have a lot of tests tied to our services and features. And you can think about, and we're going to take a look at an example here in a second, but if we had a monolithic application, the number of tests that we need to run and we need to do regression testing around, if we have a monolith with, say, 100 features in it, even if we only changed one of those features, we really should be regression testing all of it. So the surface area of what we have to test during a deployment, what we have to test before doing the deployment on a monolithic application, is quite a large surface area. And so if we have smaller independent services that are independently deployable, the surface area of what we have to test and regression test becomes much smaller and more nimble. Second point is around resilience. So the idea of microservices is let's say that like the example application that we're going to be building in these videos is related to shopping, and let's say that for some reason our inventory module is currently unhealthy, or our microservice that is in charge of managing inventory is having an issue. The goal is that, okay, if that service is unavailable, we don't want that to bring down the entire application and all of its functionality. So if we had a monolith and there was some sort of bug that was, causing the application to crash, the whole monolith comes down, right? Every service and every piece of feature and functionality that we have in the monolith is coming down with it. Whereas if we separate into microservices and we have a particular microservice that is unhealthy and crashing, we haven't necessarily brought down the entire deck of cards with it. Next item is scalability. So if we have multiple microservices, we can scale them. So if we have a particular microservice that just requires more CPU and more RAM and more horsepower in general relative to the other areas of the application, we can scale that independently. In the monolith, if we need more RAM or CPU for one feature or a couple features within the monolith, then we've got to scale the whole monolith. The whole thing's got to have RAM or CPU added to it. Whereas with the microservices, we can be more strategic about where we're adding additional CPU and memory resources at a microservice level. And then technology heterogeneity, which would mean, within a microservice, when you're going to solve a certain problem, there might be a particular language, or there might be a particular framework, there might be a particular database that all lend themselves to solving the problem really, really well. And you don't want to necessarily say that every microservice has to use every microservice has to use the same programming language, and you don't want to do that, and you want to be able to use whatever the best tools are for solving the problem. So each microservice could, in theory, have its own independent, be using a different language, whatever language is best suited to the problem. And again, because they're smaller and nimbler, the areas where you have to dedicate to using that particular language, which might be advantageous for a given feature, you're not saying you have to make that choice at the monolithic layer, that everything's going to be written using that language. All right, so what I have here are two slides. We're going to take a look at this one here, the monolith version of sort of the shopping application that we're theoretically, not theoretically, we're actually going to build, but sort of the model of what it would look like as an monolith, right? So we have some sort of front-end web application. Could be others as well, like a mobile application as well. But on the back end, we have this monolith, right? We have this one big application that's running as a service, as a process, has CPU, RAM, all of that good stuff, and all of these different areas of concern about the domain or the business, like the catalog, which is going to be a list of the products we sell, the inventory, how much of every product do we have, the shopping carts, accounts, shipping, ordering, and recommendations. All of this is just running in the same application. So if I go in to make a change, if I'm a developer and I have to make a change to, say, the catalog feature, my intention is not to disrupt any of the other features around inventory, shopping cart, and etc. But there's all the chance in the world I could, right? That I accidentally introduce some sort of breaking change because it's all part of the same code base. And also, as I was saying before, when it comes to testing, if I've made a change to the catalog area, I should really, for critical applications in the enterprise, be regression testing to make sure that even though my change was only in the catalog area, that I haven't inadvertently broken anything. So from a testing perspective, I got to rerun all my tests across the entire monolith, and I can't just focus them on a particular area, really. And then one last thing to point out is on the lower right-hand corner, you can see there's a database, right? So the monolith has, in most cases, monolith applications will have a single database that all of these feature areas all read and write to. So all of the information across the catalog, inventory, shopping cart, etc. is all written to a single database and retrieved from a single database, and you end up with this monolithic style. So what's the alternative microservice approach look like? This may look a little busy, but It's basically the same exact diagram, and we can flip back and forth a couple times here, but the same diagram because we have each area of concern: catalog, inventory, shopping cart, etc. But now each of those is an independent microservice. And you'll notice that off of each microservice there's a database, because one of the number one rules is we do not want coupling between the microservices. And if there's more than one microservice that share a database, they're now coupled. So if you make a change or a schema change to the database, that should not impact or affect another microservice. And so in microservices should not be reading or writing to some other microservices database. So each microservice will have its own persistence area. Could be one database, multiple databases, but they own them. So the catalog microservice owns its database. No one is allowed to, outside of the catalog microservice, read or write to that database. Any information that needs to be shared, we'll talk about that. And then the other major difference, there's two more major differences. On the right hand side of the diagram, we can see the event bus. So I just mentioned that, okay, there are times where the inventory microservice will need to know when some new product has been introduced in the catalog, because now we've got to track inventory for it. So how in the world is it going to know that a new item has been added to the catalog? Well, it does that through events. And we're going to talk about that. And we talked about it a bit in our domain-driven design presentation. We talked about domain events and integration events. Integration events are what leave a particular microservice, go over the event bus, and alert other microservices about something of interest that has occurred. So when the catalog has a new product added to it, it can issue an integration event out onto the event bus, and anybody that cares, one of the microservices that would care would be the inventory microservice. Could be subscribing to listen for those product created events, and when a new one has been issued on the event bus, the inventory microservice can say, oh, okay, great, I'll go ahead and now start tracking inventory for that item. And there might be others as well. So it's a publish and subscribe method, and it's not, the catalog service microservice doesn't even know who's on the other end listening. When it issues an integration event, it's just issuing the event. It doesn't know if there's anyone listening on the other side. There might be nobody, there might be every microservice on the other side listening because it cares. One other really important thing about this is that communication then is happening over the event bus, and that's an asynchronous pattern, meaning if the front end, an admin has gone into the catalog service, has created a new product in the front end, we have to send that to the back end, and we have to wait for the transaction to complete before we let the front end user know, hey, successful. Well, that whole transaction should hit the catalog microservice. The catalog microservice should update its database. It should issue the integration event and then immediately say success. We don't know who else is going to grab that integration event. And so that integration event is an asynchronous piece, meaning it goes out onto the event bus, and we don't wait for any sort of response. We just issue the integration event and move on. This is really important because what would the alternative be? Well, an alternative would be if the catalog microservice knew about the inventory microservice. The catalog microservice might actually send an HTTP request to some sort of endpoint in the inventory microservice saying, hey, I just had a new product created. I need you to take this and do something with it. And if that were an HTTP call, a couple problems with that. First is the HTTP call is a request response. So from the pattern of the actual call, it is a synchronous call. Meaning that you're sitting there waiting for a response, and we don't want that. The inventory service might be in the middle of rebooting, and so, or it may be down because there's some sort of bug in it. So we want the catalog service to be able to issue an event saying the product got created. I don't know who's interested, but here's the event. And if the inventory service is interested, which it is, and is currently not running, that's okay, because it'll be sitting in its event queue on the event bus, and when the inventory service eventually comes back up, it will see the event and react to it. So we want all communication between microservices to be asynchronous, using the event bus. And then that also means that there are times where a particular call by an end user a call might be going into, say, the shopping cart microservice to say, show me everything I have in my shopping cart, and we want to be able to show the names of the products they have in their shopping cart. Well, the actual names of the products are sitting in the catalog microservice. So how do we do that? Well, do we say that the shopping cart, when answering the request from the front end, should call real time into the catalog microservice to get the product names? The answer is no, for a couple of reasons. First is, that's a slower request process. Also, again, back to the same argument, what if the catalog service isn't running? What if it's in the middle of rebooting? We don't want those kinds of dependencies. And that's another area where the word autonomous comes in. So the shopping cart should be able to respond to a front-end request autonomously. It should not have to rely on other microservices to fulfill that request. So how do we get the names of products into the shopping cart microservice? Well, again, the shopping cart microservice is going to subscribe to events on the event bus, looking for integration events coming out of the catalog to say when a product is what the product ID is and what the name is, and it will locally store information about the products in the shopping cart microservice. So we're duplicating certain information at that point. We're duplicating product names and IDs in the catalog service and the shopping cart service and potentially others, but that's totally okay in the microservice world. We want the microservices to be able to independently and autonomously respond to requests, and in order to do that, yes, we got to ship some data around and copy it in multiple places, but that's a-okay in the microservice approach. So, rules to follow. I would actually personally mark all of these as must, but I figured the first one we absolutely want to do, which is we want every microservice to have its own database, as we talked about. No shared databases between microservices. The other ones, like I said, I typically use these as musts, but I wanted to be a little loose here because there are rare edge cases where it may not be must, and it's more of a recommendation. But communication between microservices is done via asynchronous messaging. Coming back to this real quick, what does that mean? Well, that means what we were talking about on the event bus, meaning if the catalog service needs to let other microservices know that something of interest has changed, it throws an event on to the event bus, which is asynchronous. It's not waiting for any kind of response. It publishes the event and moves on. It also means that the other microservices which are ingesting are asynchronous as well. Again, if they're down in the middle of rebooting or have a bug, once they come back up, they'll grab the events and play catch up on any events that that were issued while it was out. And okay, when responding to a request, a microservice does not need to make HTTP calls to any other microservices. We talked about that, meaning we don't want, when we're responding to a front end request, that a microservice should not have to call any other microservice to fulfill the request. It should have the data it needs locally to be able to fulfill the request. Keep microservices small and cohesive. The smaller the microservice, and the more, it's almost equivalent to the single responsibility theory, which is, be really good at doing a particular responsibility really well, and focus on that, so that now the microservices, if they're heavily focused on a certain area, you can have a team dedicated to it, or if the cohesiveness of the features that are within a microservice are all the same, then they're likely to change together. If we need to make a change to our recommendation engine, how we recommend products to our shoppers, there might be multiple features that go into that, but they're all going to be in the recommendation service, microservice. So again, making sure that they're small and cohesive. Cohesive meaning that the features that they do have are all related and are likely to change together. And then finally, use domain-driven design, bounded context principles to identify microservice boundaries. So a lot of times the discussion comes up of, what's the right boundary of a microservice? When is it too big, too small? When do I have the right things in the microservices versus not? A lot of that, I think, is easily told from the bounded context conversation. It's also told from what I was just mentioning about how similar are the features and are they likely to change together, so that, ideally, if we had to change our recommendation engine, we only have to impact one microservice. If we made this business decision of our recommendation engine needs to be improved in some capacity, that we're hopefully not, that change does not impact a bunch of microservices, that we can handle that within the context of a single microservice. So, and then the other thing, another sniff test is, again, back to the golden rule of, am I able to work on a feature, fix a feature, enhance a feature, deploy that feature without having to touch other microservices? If the answer is no, then you might want to look at your microservice boundaries again to make sure that you have the right things, and you've created the right seams for the boundaries. All right, so that's a lot of theory. Try to keep it as short as possible, and then in our upcoming videos, we're actually going to start ripping the band-aid off and actually start writing some code. So looking forward. Time for a shameless plug for my personal LLC, Keystone Code. I've been doing software development for 20 plus years now, and I've been lucky enough that I've played a lot of the different roles that go into software development, from back-end developer, front-end developer, full-stack developer, team lead, head of engineering, chief technology officer, business analyst, and architect. So if your agency or company has any needs across those different areas, whether it be a need from just understanding what those roles are, or have a need to fill one of those roles, either from a training perspective, a mentor perspective, or an actual hands-on perspective, feel free to reach out. So I can be reached at my email address, dmichael@keystonecode.com, or on the website at keystonecode.com. Thanks.